All right, we're getting near the end here. Uh, we have just two more sections after this one, so let's get going. Here we're going with polar coordinates and how we're going to do this. And essentially, the idea is that instead of defining things according to an x and y, how far out you go on x and then how up high you go on y. So, that's what we would do before. We'd say, hey, let's go, some distance in x and then up or down some distance in y, and we'd have the point x, y, like that. Instead, what we're going to look at doing is basically doing a radius and an angle. And so instead, what we're going to do is say, all right, we're going to go out a certain radius, okay, r, and then we're going to rotate that around an angle theta to match some point there. And it could end up being the same point as any other xy. We can just express it that way, and your theta can go all the way around and go positives, negatives. You can go positive, negative r values and stuff like that. But it's basically telling you a distance to go out and then where to rotate to. And so our points in polar coordinates are going to be of the form r and then some theta. So r being the radius directed from the origin, and then out to p, however far it is. So like if we're looking right here, that distance is still r. And then theta is going to be the angle directed away from the x-axis, the initial ray. So that's going to be right here. So you see here's r and here is theta. And we can basically come up with any point that we could have in the other direction. Okay? And the other thing about this, a little different, is they're not unique. For any single point, you can basically have an infinite number of polar coordinates that define it. For example, this here, 2 pi over 6, this coordinate right here would be go out 2 and then rotate around pi over 6, which is what's going on right there. And that'll get us to that point. The other thing you could do is go out 2 and then rotate this way a negative 11 pi over 6, and that'd get us there. And we can do stuff like that. And there's other ways you could do it as well, and you'll see that we basically have an infinite number of ways to do these for any point. You can also have negative values, so I could go pi over 6 and then have a radius of something, but then also some radius r. But I could also do that radius r over here and go 7 pi over 6 around this way, or I could do a negative radius and go just to pi over 6. So I could go to here and then have a negative radius that's going to take me back this way. But anyway, I'm making a mess there. I'll show that more as we go along when we see some examples here. So let's keep going. So let's look at a few points on here. Let's try the point 3, 0. We'll get some colors going. So we'll do 3, 0. And so that's going to be a radius of 3, and then no angle. So we'll go out 1, 2, 3 right to there, and there is 3, 0. Go to our next color, blue, and let's try 2 pi over 3. So you go out to 2, and then you rotate around 2 pi over 3. So this would be a pi over 3, and then 2 pi over 3 is going to put us right there. We've got the nice angle measurements right there for us to see. And there's 2 pi over 3. Next, let's try negative 4 pi. So what we're going to basically do is rotate to pi and then go negative 4. So if we go out 1, 2, 3, 4, we go out to here, we'll rotate all the way around to pi, like that. That puts us over here, but we don't want this positive pi, this positive 4, we want negative 4. So we're going to, instead of going out here to 4, we're going to basically go out here. That was just a 3 though. Out to here to 4. Another way to think of that, if you wanted, would be to, so here it is right there, would be to do a negative 4, 1, 2, 3, 4, out to here, and then rotate yourself around pi from there, always rotating counterclockwise for positive values. So either way, you end up over there. Whether you do the radius first, then the theta, or do the theta, then the radius, it's going to get you to the same point. All right, let's pick our next color. We'll go with green here. And let's do 2 pi over 3. And so we'll go out to 2, which is here, and then to pi over 3 right there. All right, so that was 2 and then pi over 3. Okay, so I drew this radius out and then rotated it up to here, to 2 pi over 3. All right, let's try another one. Let's try a different color. Let's go with, we'll do this blue. Let's do -6 and then 2 pi over 3. So again, we have a negative radius, so whichever way you want to think of it. If we rotate to 2 pi over 3, that rotates us around to here, and then we're going to want to go a -6. So instead of going out 1, 2, 3, 4, 5, 6 this way, what we're going to do is go in the negative direction. Negative 1, 2, 3, 4, 5, 6. And that'll be our point right there. -2 pi, or -6, 2 pi over 3. And then the last one, let's try -4, pi over 3, because we can have them both be negative. And so we can go a -pi over 3, which is this rotation here, -pi over 3, and then go back -4. So we'll follow this ray backwards, 1, 2, 3, 4, and we end up right there. Okay, get rid of those actual lines. So there's where all those points are. Try and see if they make sense to you, and make sure. So a lot of times what I basically do is just, go to a theta and then rotate around to it, and then do my radius. But, positive, negatives, you can rotate backwards and all that kind of stuff. Just remember, counterclockwise rotations are positive, clockwise rotations are negative. All right, here, find all polar coordinates of the point 2 pi 2 and then pi over 6. So if you think about this, we can have any version of pi over 6 that has an extra 2 pi added onto it. So we could go pi over 6, or we could go 2 pi and then another pi over 6, or 4 pi and then another pi over 6, or anything like that, even the -2 pi's. So what we can do is we can essentially say we have points, any of that are of the form 2 pi over 6 plus 2 pi n, where n is going to be 0, plus or minus 1, plus or minus 2, so on and so forth. Those will get us. And we can actually have a negative radius as well. And then when we have a negative radius, what we're going to have to do is we can go a -5 pi over 6 or a +7 pi over 6, whichever way we want to go. But let's go with the -5 pi over 6. That gets us to the same place over there. And when we get that -5 pi over 6, we just then step back a -2 instead of a +2. And then we can also have any version of that 2 pi over n. So we could go 2 pi and then back a -5 pi over 6 and get to our point where we need to be. So we'll do that plus 2 pi n, again having the same two n's for there. Okay? And so that basically is going to give us all the possible points that we'll end up getting there. I guess we could do the 7 pi over 6 one, but that's the same thing as that. You just need the plus 2n pi on there as well. Okay, so let's try some of these. Graph the following. R equals 1. So at R equals 1, we can zoom right in on there. There is 1, and there is R equals 1. The next one they want us to do is R equals -1. So this is everywhere that R equals -1. So essentially, we're stepping back here and then going around 2 pi. So there's R equals 1 and R equals -1. They give us the same circle. Notice this is different than when we were doing something like x equals, 3. X equals 3 would just be a vertical line. R equals 3 is a circle. R equals some constant in a circle, X equals constant is a vertical line, so they're a little different there. Over here we've got theta equals some angle, and it's always this same angle, and there's no restriction on what the radius could be. Therefore, this just tells us go to pi over 6, and any radius you want, positive or negative, is going to work. And so you end up getting a straight line. And the same thing for 7 pi over 6. It's going to give you the same line. You're just going around to 7 pi over 6 and then doing positive. So one we went to pi over 6, and the other we're going around to 7 pi over 6. But either way, it's just a straight line from there. Okay? So that gives us a straight line, whereas if we had, y equals something, that'd be a horizontal line, or over here, whatever. So just having one of our variables equal something is a little different than it was in the Cartesian coordinates that we had been doing. Okay, let's take a look at example 3 here. Graph the set of all points whose polar coordinates satisfy this. So everything that fits here. So let's take a look. 1, we need the radius to be greater than or equal to 1 and less than or equal to 2. So that means if I do this, let's make this green and this pink. So what I can do is come back over here with green and say, here's 1, r equals 1. And the other one I believe I did in this pink, here's r equals, oops, I got off of it there. Here's r equals 2, right there. And then it tells us we need all theta between 0 and pi. So we're going to do, we'll do a, this, no, I don't want to use green. I already used green. Let's do blue. Okay, so we have to stay between blue and, I think this tan might show up a little better, and the tan, the brown there. So let's start with blue. This is going to be an angle of 0, so we have to stay between this angle. This is our 0 angle. And then we have to go all the way up to, oh, I don't have a brown. I thought I had a brown. Well, I guess I'll change it to yellow. And then all the way up to this angle right here in yellow. So here, let me re-highlight that to yellow. There you go. All right, and so we have to stay between those two angles, which means ultimately our result is right here in this area. Okay? Maybe I could have just actually highlighted that a little bit better than I did with that. I'll use the brown for that. So we're in this little area right in here. All those points there would satisfy that. Okay, this next one is r is between -3 and 2, and theta is pi over 4. So we go to pi over 4. Pi over 4, I'm just going to color it in blue. So pi over 4, that's this. All that right there, that's the pi over 4 angle. And then we need to stay between -3, which I'll do in green. So -3, that goes back 1, 2, 3, that's here. And then here, and then +2, which I'll do in this pink, +2. So our result here, do this in red, is here, all the way up to and including here. Those two radii are inclusive. And so that takes care of that one for me. All right, let's take a look at this next one. We just need anything between the angle 2 pi over 3. Do that in pink. So 2 pi over 3, both here, and then we also need to consider that we can have negative radii. So that angle continues on that way. And then also 5 pi over 5. All right, and that's just pi. And then also for the negative radii there. And so we ultimately end up with being in between these two, right in here and right over here. All of those points between those two lines. Okay? Now, how do we relate these two Cartesian coordinates? We should be able to switch back and forth because essentially any function we write in one, we should be able to get going in the other. Although there are a little different types of functions here. So let's take a look at this. So in Cartesian coordinates, we always treated y as the dependent variable, x as the independent. Here, what we're doing is r as functions of y. So we had f of x, right? That was equal to y. Here, what we're doing is we're doing r of theta, all right? That's going to equal our radius is going to be a function of theta. All right, so theta is going to be, sorry if you hear that bird in the background, theta is going to be our independent variable, and then r is going to depend on it in the way we're doing this. So x is equal to r cosine of theta, and y is equal to r sine theta. That you can get just simply by viewing your sines and cosines, right? Cosine theta is x over r, so just multiply both sides by r. And do the same thing for sine, and you can get that as well. Then we can also do Pythagorean theorem, x squared plus y squared equals r squared. That helps. And then another one you can do is tangent of theta is equal to y over x. So there are our relationships just from our basic little trig functions right there in Pythagorean theorem. All right, and then here you go. Here are some polar equations and then the Cartesian equivalent ones. Take a look through those and see if you could go between the two of them. Now, sometimes what you'll notice, and the whole point of this is, for example, if you look at this one, this equation is much simpler than this one. And so sometimes when you get something that's really complicated, it can do you a world of benefit to actually move to polar coordinates. This happens a lot in things like what I've studied physics, is whenever you have something that's like circular type symmetry, dealing with planets or things like that. If you notice, there's a lot of circle stuff out there, a lot of spherical stuff. And you can even go one further step into the extension of this, which is spherical coordinates, where you have a radius and then you have two angles. You have a radius and a theta, and that gives you like the circles we're getting here, and then you can rotate up out of the plane like in the x or the z direction and go up to like three-dimensional points and rotate around. So you can do r, theta, and phi. But you get these spherical or circular symmetries, and it helps a lot. But then other times going in Cartesian is simpler, especially if you're working on something that has, like squares and rectangle type symmetries in them. Then that one will actually be a lot simpler. Okay, so let's take a look here. It says find a polar equation for the circle x plus y minus 3 squared equals 9, or x squared, sorry. So we can start with that. X squared plus, and then what I'm going to do is expand this y minus 3. I'm going to square it. So it's going to be a y squared, and then a negative 6y, and then a plus 9 equals 9. I can subtract 9 from both sides and go ahead and get a 0 here on the right. I can group this x squared plus y squared together right there, like that. And remember, x squared plus y squared is r squared. So I'm going to go ahead and use that and make my first substitution. There's r squared. And then what I'm going to do is say this is 6y, and y, if you remember, is r sine theta. So this will be minus 6 times r sine theta right there. And then that equals 0. I can factor out an r and have r times r minus 6 sine theta. Remember, we want r as a function of theta, so we need to isolate r. And so then, well, if we can, and then we've got equals 0, and then we go ahead and start figuring stuff out. R equals 0 is going to be an answer for us from that right there. And then we have this other part to get 0, which is where r minus 6 sine of theta equals 0, which means r equals 6 sine theta. All right, and so there we go. That's what we're going to have, and you can see right there that this is essentially our function, r equals 6 sine theta. And there's a picture of it for you. Okay. If you do have a grand calculator, you can go in there, put it in the polar mode, and actually type in r equals 6 sine theta and see that you get the same thing as if you graph the other one. Although the other ones, it's not a function of x, so that's not going to work. But you could do it in two pieces, a plus and a minus part. All right, so replace the following polar equations by equivalent Cartesian equations. So here we have r cosine theta. R cosine theta, go back 2 pages, that's just x. So we'll come over here. I don't want to leave those there. Let me get rid of those. So we'll come back, and we've got, this is x equals -4. And if you graph that, it's just a 1, 2, 3, 4, and there's your line right there. Okay, and that's it. Next one, r squared equals 4r cosine theta. So r squared is x squared plus y squared, and r cosine theta is just x, so 4x. And then it's up to you if you want to go through. We can go through and you can do completing the square. I'm going to leave that for you. If you have issues with completing the square, then just meet me on Zoom and I'll walk you through how to complete the square. But go through, complete the square. All right, you have to do it for x. Really, you don't have to do it for y. Normally you would, but y, there's no other y's in it, so there's no need to complete the square for y. If there was any, like, see how there's an x squared and an x, you'd have to complete the square for x. If there was a y, like something times y over here, you'd have to complete the square in y as well. But you don't have to. But go through, complete the square, and you'll get x minus 2 squared plus y squared equals 4. And so this is just a circle with a center at 2, 0. All right, 2, and then this is y minus 0, so that's, that's why we get the 0 there. And it has a radius equal to the square root of 4, which is just 2 in this case. And so you'd get something like at 0, 2, 1, 2. There's our center, and then it would have a radius of 2, so it would come around it like that. Okay, something like that. I probably could have done that better. Up 2, down 2, right 2, here. So we're going to have a circle like that. Okay, and there was the center. Okay, let's try this next one. Actually, what I'm going to do is leave that very last one for you, but I will put it in the notes. You could do it in about 4 lines, 3 or 4 lines, depending on how good you are at this. So give that a try, and that's, I think, just making sure. Yep. Oh, I didn't mean to double that page. That's pretty much it for this.